Hello, Chemistry 1A, and welcome to a Zoom recording. In this recording, I'm going to be reviewing the expectations for graphs. So these expectations are applicable to everything that you are going to complete in Chemistry 1A and 1B and 1C for that matter. And so again, I want to set some expectations here. The first thing I'm going to do is I'm going to navigate to Canvas where I have some of these files. So let me share screen and get moving over there. There we go. Should be sharing now. And opening up Canvas. And of course, getting to our course. And note that these are posted here in the file section. So I'm going to open that. And you see there is a file here called graphing example. Also later on, if you need a piece of graph paper and don't have one, of course, you can go here for a printable piece of graph paper. So I'm going to open up this document and we'll walk through how it was prepared. Let me shrink this down a little bit so I can get it all on screen. You may want to go and print out a copy of this or otherwise take a look at it if this looks a little bit small. There, I've got it all on screen. The first thing I want to point out, of course, is that a graph starts after a set of data is obtained. So what we see over here, where I've got my cursor, is a set of data. And this data happens to be some density data, not unlike what you're going to do in the first HOL experiment. Or again, perhaps it's the second one. Note here on this column, I have mass, and it's a little bit small, but right here I have in grams. And that means that everything entered into the column has those units. Information, data, if you will, without units is just a number. So all data has to have units associated with it, either directly written after it or in a column like this, where the column is labeled as to the data. So this data is a set of mass versus volume of a particular liquid. So there's the data that we're going to graph. The first thing I'm going to review is the scale on the graph. Before I get going with that, let me comment a little bit on computer-generated graphs. If you are capable of using Microsoft Excel or Google Sheets, I guess it is, for the preparation of graphs, that's great, as long as they end up looking like or conforming to the requirements that I'm specifying. It's been my experience that most students don't know how to use those tools to prepare a proper graph. In any event, I don't really care, but ultimately this is the expectations for the graph. And there's going to be plenty of situations where you're going to need to put it in your graph book in any event. So the first thing I want to point out is graphs are of the format where they are titled Y versus, and pardon me for having left X out over here, this should say Y versus X. And this is mass of the unknown versus the volume. So we can see I have mass on the Y-axis and just a little bit off screen, there it is volume on the X-axis. So mass versus volume. Note that my mass data goes from, I've got 10 here up to about 53 or 0 to about 53. So on my Y-axis, I'm going to stretch out the axis so as to capture as much of the paper as possible. It would be silly to call each one of these squares 10 and go 0, 10, 20, 30, 40, 50, and try to squeeze everything in here. So choose a scale that expands the axis as much as possible. Note that this graph paper, I have allowed 5 squares equals 10 grams, or another way is 1 division, 1 square equals 2.0 grams. I've titled my axis as mass of the unknown and created the scale. Likewise, I've done here, my volume goes from 0 to 50, But note that I've got about 38 squares on here. There's no convenient scale that expands 50 into 38. So I've chosen a scale that expands this to use most of the paper, 2/3, 3/4 of the paper or so. And since we live in a decimal systems, divisions by 5 and 10 tend to be a whole lot easier. So note I've got 1, 2, 3, 4, 5 divisions equals 10 milliliters, or just off scale, 1 division equals 2 milliliters. If you are using graph paper that might have 10 squares to the inch or 4 squares to the inch or some other sizing, your scales will certainly be different. And my x-axis has a label, volume on the x-axis. So those are the titles of the graph that I expect. I expect the axes to be labeled. I expect divisions or scale to be noted. Now let's move on to the graphing of the data. So I expect this is old hat, but I find that sometimes it's not for some people. So I have simply, here's my XY data point. This is 10.8 grams. I put a little X here, right there is 10 milliliters. So I'm just, these small X's are the data points. I probably should have made these data points a little bit bigger, meaning making the X a little bit bigger so that it's going to be seen. But there they are. So I plotted my 1, 2, 3, 4, 5 data points. Now, this data is expected to be a straight line, which is generally our goal, because straight lines are a lot more easier to interpret than our curves of some form or another. So I have drawn a straight line in a process simply eyeballing it. In other words, I put a straight edge on here and tried to find a line that got as close to these data points as possible without biasing towards any one of them. And you can see this point is a little above, this is a little above, that's a little above, that's a tiny bit below, that's a tiny bit below. So I've come pretty close to that. But again, all I did is I put the straight edge on there and I drew the best straight line I could reasonably manage by doing so. As I said, it is most often convenient when our graphs are straight lines, as this one is. It is also particularly helpful in many, many cases to understand what the slope of that line is. Pardon me for just one moment. I'm back. So here we are. We see that I'm looking to obtain the slope of this line. This circle right here and this circle way down here represent 2 points on the line. Please note, this line did not go through the origin or the point 0, 0. Do not force your data through the origin. It is no more or less a valid data point than anything else. And forcing it through, meaning making certain that the line goes through the origin, will create errors in your data. So I have selected 2 points on the line, there and there, and I have identified their coordinates. This is 48 milliliters on this line right here, and right here on the expands over to the y-axis, excuse me, at 52.4 grams. So these are the coordinates of this data point. Down here, the coordinates are 0.7 milliliters and 0 grams, because it's right there on the x-axis. So these are the data points for my second one. Back to our high school algebra, the slope of a line is the change in the y value, or the change in y divided by the change in x. Get used to these triangle signs. I use them often. They're used throughout many science disciplines. It is the capital letter D in the Greek alphabet, pronounced delta, or a change in. So this is delta y divided by delta x, or perhaps a little bit more familiarly, excuse me, it is the y coordinate, y2 minus y1. In other words, the difference in value between the coordinates of the two y values divided by the difference in the coordinates of the two x values. It doesn't matter which data point I call data point 1 and data point 2, or coordinates 1 and coordinates 2, the math will take care of the sign. So I've got y value of 52.4 right here, and y value here of 0 grams. Likewise, my x values are 48.0 milliliters and 0.7. So the slope of this line is 1.11 grams per milliliter. Slopes have units, and they need to be included. The slope of the y-axis is grams. The slope of the x-axis is milliliters. So again, slope of 1.11 grams per milliliter. Another common error that I wish you to avoid, and that is this. Pardon me for a moment, I had it in the top of my head. No, I guess not. So I think we're good there. So this is what I expect for graphs. Now, I've graphed mass versus volume. We're going to have data of varying different kinds, but this is pretty typical. And again, this is what I expect. Now, let me go on to something else, which I don't expect that you do, but I strongly urge anybody going on in the sciences, chemistry, physics, engineering, to learn another technique, and that is this. So my guess is that most of you have TI-84, TI-85 graphing calculators, or if not a TI calculator, some Casio or similarly programmable and graphing calculator. They all perform what is referred to as a least squares analysis, or sometimes a regression analysis. You should look into the manual for your calculator, which I suspect nobody has because that tends to get thrown away with all of the packaging. You can, I'm sure, find it online by simply typing in TI-84 manual or some such thing and looking up least squares results. What this does is provide you a way to enter the data, this data, in a prescribed format, entering X and Y data in a way that the calculator will accept it. The calculator will then give you the results. In other words, it will calculate the slope for you. So I did this using least squares calculation, and I got a slope of 1.072 grams per milliliter. And I contrast that with the 1.1 grams per milliliter when I did it by hand, if you will. So they're certainly very close. The calculator is probably, well, it's not probably, it is more correct, but this is also a common and accepted method. It also provides the X and Y intercepts for the data, and the calculator will also provide what is referred to as R square or squared, sometimes referred to as the correlation coefficient. This correlation coefficient is an indicator of how closely the data approximates a straight line. And in this case, the calculator was 0.9997, which means it approaches very, very close to a straight line, which is entirely consistent with our observation that yes, in fact, these data points are very close to a straight line. If they were exactly on the line, absolutely exactly every one of them, then the correlation coefficient would be +1. Okay, let me also provide simply another way of determining the average. And I guess I should back up here. You're all familiar with simple arithmetic averages, I hope anyway. The slope of a line is another way of implying or another way of representing the average. In other words, this data is looking for ultimately what is the density of this unknown liquid. And I have 5 data points. Each one I could calculate the density from, and I'm going to do that at the bottom of this page. And then I could calculate the average density, giving me a set of data or a set of average. In this case, the slope, 1.11, represents the density of the liquid in the units of grams per milliliter, which are very, very common units for liquids. So what did I mean by averages? So note that this data right here is the same data that was in that table. And if I take 10.8 divided by 10, of course, I get 1.08 grams per milliliter. And likewise, so each one of those separate data points can be used to calculate the density of that liquid. And I've got them all right here. And see, they are all very nearly the same, not exactly, but they are very nearly the same. And so if I take these and then do a simple arithmetic average, this symbol is a Greek S, capital S for sigma. And so this means the sum, right? S for sigma, S for sum, divided by 5, the total number of data points, and the average 1.087 grams per milliliter. And yes, I know I'm using one too many significant figures, but that's a discussion for a different time. And the average is 1.087 grams per milliliter. I'm going to give you yet another one. I could sum up all of these masses, 10.8, 22, 33, 43.2, 53.8, and I get 162.8. And I can sum up all of these volumes, 10, 20, 30, 40, 50, and get 150. And I get an average of 1.085 grams per milliliter. Now, at this point, you say, well, how can there be different values for the average when I have only one set of data? And the answer is simply, it depends on how you calculate it. And so I've calculated it in a number of different ways to indicate that, again, the value is going to differ slightly depending on how you calculate it. So when you are reporting to somebody an average or a slope or some such thing, you need to communicate to them how you have calculated it. Now, I hope that this part of the discussion hasn't added any confusion to the matter, because in almost all cases, this is specifically what I'm going to be asking for to determine the slope of the line. Let's see if there's anything else. No, that is it. I certainly hope that preparing graphs is something that you have done a lot of. You might have gotten a little bit too dependent on using a computer to do so. And there's plenty of times when that is preferred and appropriate. But there's also many times that you need to be able to do that by hand. For example, when you do the lab reports, and in a few occasions where I have graphing questions on a quiz or test. I'm going to now move to Canvas because there is an assignment posted. Scroll down. Again, your always looks a little bit different. And of course, it is labeled simply laboratory assignment number 3, graphing. It is due, pardon me while I look at my calendar, October 2nd. So that's giving us, of course, until October 2nd to get this one done. And open that up. And we see that, again, I have a set of data to graph. The assignment is basically to do what I just did, right? Title, axes labeled, eyeball or draw the best straight line that you can, calculate the slope from your eyeball best line. I am going to ask you to look up in your calculator how to use least squares regression. You could probably also Google least squares regression calculator into Google, and it would probably also find you a program that would allow you to do that. I want you to compare the slope that you get from doing the eyeball test, or basically just doing it by hand, with the value you get from least squares regression. So that's part 6, compare those slopes. You will submit as a PDF. Of course, this is needs to be completed on graph paper that's implied from it. And again, ultimately submit that as a PDF document. That is the end of our discussion here. I will post, this will be posted soon. And if you've got any questions, as always, bring them up. We'll talk to you later.